Hey, what's up, everybody? It's Miss Brothers. Hey, we are going through, I'm just walking you through the Unit 2 phase change and energy test review. This is the key, and I just wanted to kind of talk to you about some things as we walk through this, okay? So, like I said before, this is 7 parts to this review. With part 1, you're just reviewing that Unit 2 vocabulary, and I've actually given you an assignment on Google Classroom that's due tomorrow that is asking you just to roll through those vocabulary words and make sure that you know them, go through the learn function, go through the flashcards, and then show me that you've achieved mastery on those vocabulary words. That becomes really important because if you don't know the words, it makes it much harder to do just do the work because you're a little bit lost on what it is being asked of you, okay? So as far as part two is the language of phase change, nouns, verbs, that chart that we put together about nouns being the states of matter, gases, solids, liquids, and verbs being what they do when we add or take energy away. Do they freeze? Do they melt? Do they sublime? Do they deposit? Those sorts of things. So for the first one, it says number 1, and I'm specifically on this question right here. It says describe the arrangement of the particle type of movement of solids. Include a simple particle drawing of a solid, and that's what I've done right here. You can see my particles are close together. They're tightly packed. As far as the particle arrangement, they are tightly packed, and their movement is that they only do vibrational movement only. The next one, describe the particle movement of a liquid. Include a simple drawing of a liquid, and I've included that here. So my particles are still fairly close together. So my intermolecular forces, my IMFs in my solid are very strong. The intermolecular forces, or IMFs, in my liquids are medium or weaker. And as you can see, they're still close together, but they have the ability to roll by each other. As far as their particle arrangement for liquids, they are loosely held together. They can take the shape of their container. As far as their movement is vibrational, just like a solid. And we also add something called translational movement, which means they can sort of roll around each other. Okay, so if these are both solids, they kind of roll around each other like this. Okay, solids can't do that because they're bonded together. Number 3, describe the particle movement of a gas. Include a simple drawing. I didn't really do that because really all you would have to do is just draw them being a little bit all over the place, and those little motion lines and little arrows showing that they're able to move freely and move with quite a bit of speed. So that's going to be your particle drawing for gases. As far as their arrangement, they move freely because we no longer have those intermolecular forces or those bonds holding them together. And as far as their movement, they have all the movements of solids and liquids, so they can move vibrationally. They vibrate. They can roll past each other just like a liquid. And then we add the last piece of the puzzle is that they can also rotate. So they can rotate in circles. They have complete freedom of movement. So as far as the movement of gases, vibrational, transitional, and rotational. Question 4. Write answers to the following processes. If we are going from a solid, if we add energy and we go from a solid to a liquid, that's called melting. If we add energy to a liquid, eventually it will vaporize or boil. If we remove energy from a gas, it goes down to a liquid or condenses, otherwise known as condensation. If we continue to lose energy, we go from a liquid to a solid. That's called freezing. Sometimes we heat things up so quickly or their boiling points are so low that we have a solid that goes straight to a gas and skips the liquid phase altogether. That's called sublimation. And sometimes we have energy that is lost so quickly that we go from being a gas, skipping the liquid phase altogether, and just being little solid crystals. We see this when it gets really cold, like 20 or 30 degrees below zero, and somebody goes outside with that pot of boiling water and throws it, and it just kind of turns into this big thing of smoke. That's deposition. That's the last one. Part 3, heat transfer basics. And I'm just going to walk you through my answers and kind of explain my thinking here. It says number 1, I'm on this question right here. What is the difference between temperature and heat? And I did answer this question in one of my classes today, but this is the big difference, is that temperature is the measure of the amount of kinetic energy in matter. Heat is the process where thermal energy moves from systems of high energy towards systems of low energy. So what it really comes down to is that temperature is a measurement and heat is a process. And temperature is a measure of the motion of particles or its kinetic energy. And heat is a process where thermal energy moves from systems higher energy always towards lower energy. Next question. List and describe 3 ways thermal energy is transferred. Where those 3 ways that energy is transferred is radiation, conduction, and convection. And radiation is the transfer of energy through electromagnetic waves or rays. Conduction is the transfer of energy through direct molecular contact. And convection is the transfer of energy through heated fluids. And fluids, we're actually talking about liquids or gases. And you can see what I'm pointing to there. Number 3, when thermal energy is being transferred between solids, what method of heat transfer is being used? And that's conduction. And that's because you have to have molecules that are in contact with each other. You know, the particles in solids don't move. And so, you know, it's like when I put that ice cube on that plate that started to melt. That was a great example of solids using conduction to transfer energy. Question 4. When thermal energy is being transferred between fluids such as a liquid or gas, what method of heat transfer is used? It's convection. And again, when we're talking about fluids, we're talking about something that has the ability to move. Both gases and liquids can do that. And convection is how things are heated using conduction in order to move that energy around. So if it's a fluid, it's convection. If it's a solid, it's conduction. My last question, here I am on page 2, and I'm looking at number 5, which is right here. Sorry, this is a little convoluted. We're just looking at the key that's in my notebook right now. Number 5, true or false? Circle or highlight one of these. Radiation does not require matter in order to transfer energy. And that is a true statement. Of all of the different energy transfers, radiation, conduction, or convection, only radiation does not require matter or molecules in order to transfer energy. It's because it uses waves in order to do that. All right, part 4 is about thermal energy and specific heat. And these first ones are basically explanation problems. So let's do the first one. It says define specific heat, aka specific heat capacity. So we know it as specific heat. We also know it as specific heat capacity. And what it says is specific heat capacity of a substance is how much energy is needed to heat 1 gram of a substance 1 degree Celsius. Another way of saying this is to say how resistant is a substance to being heated. The more resistant it is, the higher its specific heat. So if you have something with a specific heat of 10 and something with a specific heat of 1, it means that the specific heat of 10 is harder to heat up. And as far as I know, I don't know if there's any substances that have specific heats that high. I should probably learn that. The next one, number 2. Water has a specific heat of 4.18 joules over grams degrees Celsius. And that, again, that's our unit for specific heat. What does this actually mean? So what it means is this. It means that 4.8 joules of energy, because remember, joules is a unit of energy, how much energy, are needed to raise, so in water's case, 4.1 joules of energy are needed to raise the temperature of 1 gram of water 1 degree Celsius. So if the temperature of 1 gram of water is 10 degrees, we need to apply 4.18 joules of energy to that gram of water if we want to go from 10 degrees to 11 degrees. But that's what we're talking about when we say specific heat of something. Okay? What's the energy number that we have to have in order to do that? Sorry guys, I'm pausing for a minute because my cat wants to come in. I'm at home right now, and so I just let my cat in. I'm not going to show her to you because I don't want to move my camera, but that's my cat Marla. It's time for her to eat. Anyway, all right, let's go to question 3. You have 2 substances, substance A with a specific heat capacity of 1.8 joules over grams degrees Celsius, and substance B with a specific heat capacity of 3.1 joules over grams degrees Celsius. Which one will require more energy to heat up 1 degree Celsius, and why? So the first thing we're asking is which one will require more energy? Well, substance B will require more energy because it has the higher specific heat. We have to apply 3.1 joules of energy to this one. We only have to apply 1.8 joule of energy to this one to get that substance to go up 1 degree. All right, question 4. You have two substances, substance A with a specific heat capacity of 1.8 joules over grams degrees Celsius, and substance B with a specific heat capacity of 3.1 joules over grams degrees Celsius. Which one will be able to heat up faster and why? So it's the same substance. In this question, we're asking which one needs more energy in order to raise its temp 1 degree. In this one, we're asking which one will heat up faster. And in this case, it's going to be substance A. Substance A only has a specific heat of 1.8, and as a result of that, we're going to need less energy to heat up substance A compared to substance B, which means that substance A is going to heat up faster. So the less energy, or the lower the specific heat, the faster the substance will normally heat up. Okay? All right. Number 5, write the symbols for the following variables. Specific heat, again, that's going to be C, and I like to write it CP. That denotes at a constant pressure. B, thermal energy, or change in thermal energy. That's always going to be our big Q. Mass is our small m, and change in temperature is our delta T. Remember, this triangle means delta, and in science, delta means change. All right, let's go to our next page. All right, part 5 is all about thermal energy and specific heat problems. Now, I'm not going to walk you specifically through these problems. We're going to talk about the answers. I will talk about the process. There's several videos on my YouTube channel with how to get through problems like this. And so those are the videos that you should be watching if you want to learn how to do thermal energy and specific heat calculations. All right, so number 1, how much heat energy would we need to be added to warm 25 grams of gold from 25 degrees Celsius to 100 degrees Celsius? Well, if we're going through our process, remember, we're trying to find how much energy, and that's when I go through my process, that's the first thing I do is to figure out what is it I'm trying to figure out. I'm trying to figure out how much energy we're going to need. So again, I'm going to start with that formula, Q equals mass times delta T times the specific heat. Now again, this is one of those times when you're going to have to manipulate that specific heat triangle. You'll have a specific heat triangle at your disposal tomorrow during the test, and it really is up to you to remember how to use it. Again, we've had lots of instruction, lots of videos where I'm showing you how to use that triangle, and again, those are the videos that you should be watching. So I go through, I figure out that the only thing I don't have is my change in temperature. I've got my mass, it's right there. I have my specific heat, it's in this chart right here, and specifically I'm looking for gold. There it is right there. It's 0.128 joules over grams degrees Celsius. And then it's just a matter of plugging in the numbers, doing the math, and in a perfect world you came up with 2400 joules. The unit for Q is always J or joules, so you want to make sure that you're using the correct units. Okay, and again, you can use that document in your notes. You should look through that over tonight. You should know those things. One of those things that you should know is the unit for Q is joules or J. Number 2 is to calculate the change in energy when 75 grams of water are cooled, and that's a significant statement right there, from 100 degrees Celsius to 27.5 degrees Celsius. So again, I'm looking for a change in energy, and if it's energy, it means Q, at least thermal energy, it means Q. So we've got mass times the change in temperature times the specific heat. We're going to take a second and we're going to find our change in temperature. The water starts at 100 degrees Celsius, so that's my TI, and then we cool it down to 27.5, that's my TF. And remember, change in temperature is TF minus TI, which means we're going to end up with a negative number for my change in temperature, and specifically we're ending up with negative 72.5. So what I have to remember is that now that means my Q is going to be a negative number. There's my little negative sign right there. So I take 75 grams times negative 72.5 times the specific heat of water, because it says right there that I'm dealing with water. And if I look at my chart, it says water has a specific heat of 4.18 joules over grams degrees Celsius. Number 3. What is the change in thermal energy when 84.77 grams of carbon, that's important, drops in temperature, so we're cooling again. Oops, I forgot to put my negative in. Watch out for that. Carbon drops in temperature to 22.4 degrees Celsius from 37.2 degrees Celsius. So again, when I go through my process, change in temperature 22.4 minus 37.2, which means I have a negative 14.8. I plug in my numbers there, and I end up with a Q of negative 88.95 joules. Now, for number 4, so the first 3 we're using that Q equation where Q equals M, change in temperature times specific heat. But you have to watch out for number 4, because in number 4 we're asking you to find the specific heat of a substance. So we have our Q right here, and we have our information so that we can get our change in temperature, but we have to use a slightly different formula. So what we have to do is we have to bust out that specific heat triangle, cover up the CP, because we don't know the CP, so we're covering it up in our triangle. And now we set up the formula Q over mass times the change in temperature. So once I calculate the change in temperature, 94.6 minus 22.4, that leaves me with a change in temperature of 72.2 degrees Celsius. When I set up my formula, I've got my Q, 1,587 joules, divided by or over 75 times 72.2 degrees Celsius. Now, one of the things I want to caution you on is that when it comes to when or how you do the math on this, I'm going to remind you that you do the parentheses first. And once we multiply the parentheses, once we multiply the mass and the change in temperature, we end up with this number right here, 5,415 grams degrees Celsius. Once I have that number, now I can take Q divided by that number. So now I can take my energy, 1,587 joules. Then I'm going to divide that by 5,415 grams degrees Celsius. And when I'm done, I'm going to have this specific heat number, which is 0.2931 joules over grams degrees Celsius. Because remember, the unit for specific heat is this funky little joules over grams degrees Celsius. Now, I didn't have you do number 5. I was working through this key earlier, and I found a mistake that doesn't allow you to do number 5 and make it make any sense. So I went ahead and crossed it out, so you don't need to worry about that. Number 6 is list the following in order based on how fast they heat up, fast to slow. So I went ahead and just put fastest at the top. Gold is my fastest, and I know that because of all of these metals that are listed, carbon, gold, iron, water, and aluminum. I guess water's not a metal. I guess these are all substances. So I've got, what, 1, 2, 3, 4. Ooh, I'm missing a substance. Which one did I miss? Ooh, I missed aluminum. Aluminum should be in here. Oop, let me do that real quick. Aluminum, you go here under carbon because you are 0.897 joules over grams degrees Celsius. Okay, that's better. Yeah, so the one that will heat up the fastest is going to be gold because it has the lowest specific heat at 0.128. And the one that's going to heat the very slowest is water because it has a specific heat of 4.18 joules over grams degrees Celsius. And in the meantime, iron will heat up the second fastest, then carbon, then aluminum, and finally water. And again, remember, you guys, the lower the specific heat, the faster it heats up. So just keep that in mind. Low specific heat means it heats up quickly. All right, number 6, we've got some interpretation to do of this graph. And you do have one of these graphs on the test, so just be aware that that's coming. So you might want to pay close attention to this. The first one is, what is the boiling point of substance B? Well, one of the things that you have to remember is you have to remember that when we're looking at phase change diagrams, the plateaus mean something. The first plateau means melting or freezing. Okay? And that doesn't matter what the substance is. If it's the first plateau, so this one is the first plateau for substance A. This one is the first plateau for substance B. And again, I can write that down, melt and freeze. This is the second plateau for, oh, and I forgot the first plateau for substance C, melting and freezing. The second plateau is where we have vaporization, otherwise known as boiling. And we also have condensation, or I'm just going to put condense. Sorry about my handwriting. It happens. This is my second plateau for substance B. So I've got vaporization / boiling. I can also say condensing or condensation. Same things here, vaporize, boil, because this is my second plateau for substance C, and condense right here. Now at the same time, now that I know what these, and I want you to notice something. You guys notice that every time I have a phase change, I've got two things happening, melting and freezing, vaporizing and condensing, melting and freezing. Every one of these plateaus, I have two different phase changes happening. Over here, I have vaporization and condensation together. Vaporization and condensation, melting, freezing, melting, freezing, melting, freezing. So remember, when I have phase change, I have two processes that are essentially happening at the same time. As far as what's happening, where my temperature is increasing again, well, right here, substance A is solid. Right here, substance B is solid. Wow, this is getting convoluted. Right here, this substance is also solid. At this point, substance A is liquid. At this point, substance C is liquid. And at this point, substance B is liquid. Okay? Once I get above my vaporization, boil, condensation, right here, my substance A is a gas. Right here, substance B is a gas. And right here, substance C is a gas. So there's a lot going on with this. These phase change diagrams tell us a lot of information. Let me simplify it for you, and I'm going to use substance A. My first plateau is where I have freezing and melting. My second plateau is where I have vaporization and boiling. If I'm below freezing and melting, I have a solid. If I'm above it, I have liquids. If I'm above vaporization and boiling, I have a gas. And if I'm below vaporization and condensation, I have a liquid. Okay? So like I said, there's a lot going on there, but if we understand what's happening at these plateaus and in between in the phase change diagram, that's what's going on. Okay, so let's look at number 7. Number 7 is, what is the boiling point in degrees Celsius of substance B? Well, substance B is this dashed line right here. And so what we're looking for is, we are looking for, where does the plateau begin for substance B? And if I'm looking at this, it looks to be about, each one of these lines above 300 is about 33 degrees. So if I'm looking at this line right here, this plateau line, because that's where my boiling or my vaporization is taking place. And remember, boiling point and vaporization are the same point. It's that we use those terms interchangeably. So if I'm looking, the closest I can figure out really is about 335 degrees Celsius. Number 8, what is the melting point in degrees Celsius of substance A? Well, substance A, the melting point in degrees Celsius, so if I'm looking for substance A, it's right here, and it's sitting along this entire line right here. So this entire line is sitting at about 100 degrees. Okay, so it starts right about here, carries on about here, and stays at about 100 degrees Celsius. So at number 9, it looks like I didn't actually answer number 9. I guess I better do that. Describe substance C at 250 seconds. Well, here's 250 seconds right here. And if I come right up the line, okay, and at 250 seconds, what I have here is, well, actually, you know what? I meant to put that right there. Boop. Sorry. It should have been right here. At C, at 250 seconds, is vaporizing or condensing. That's what's happening. Part of substance C is going to be a liquid. Part of substance C is probably going to be a gas at that point. But that's what's happening at 250 seconds. So I screwed that up. What phase of matter is substance C at 100 degrees? Well, here's substance C right here at 100 degrees. And so what we have here, it's both liquid and solid at 100 degrees. It's doing both at that point. Okay. Number 11, what is the strength of the IMFs, or intermolecular forces, of substance B at 10 seconds? Well, here's substance B, And at about 10 seconds, we are very much a solid, which means that the intermolecular forces are really strong. All right, number 12. How long does it take before substance B begins to boil? And if we look at that, substance B begins to boil. Oh, there you are, substance B. It begins its boil at about, and if we bring this straight down, it's about 240 seconds. Okay, and that's what I've written there. Number 13, which substance will have liquid particles present after 100 seconds? Explain. Well, if I look at 100 seconds, so 100 seconds is right here for substance B. It's right here for substance C, and it's right here for substance A. So the question is, which substances have liquid particles present at 100 seconds? And the answer is all of them. Here's substance B. It's in that melting, freezing section, so we know we're going to have both solids and liquids there. Same thing with substance C. Both solids and liquids are going to be here. And if I move up the line to substance A, I'm still on that line where substance A is a liquid. It hasn't converted, it hasn't started that vaporization process yet. So substance A is completely liquid at 100 seconds. Question 14. Describe the molecular arrangement and motion of substance A at 50 degrees. So let's go to 50 degrees, which is right here on my graph. And if I bring this up to substance A, right here, I'm on that melting and freezing plateau. So what I wrote was, at 50 degrees, the molecular arrangement of substance A is either tightly packed if it's still solid, or loosely gathered if it's a liquid. The motion is likely vibrational or vibrational and translational, depending on whether it's a solid or a liquid. Number 15. Now I just want you to know the questions on the test aren't quite as complicated as you're seeing on the review. But if you can answer these review questions, then you can answer the test questions because they're multiple choice. Number 15. What substance has the highest specific heat? Explain your thinking. What you're looking for is, if we were to say which one of these is showing that it's the fastest to heat, and one of the things that we're looking for is these lines right here and how soon we get there. So for instance, this one heats. It heats quite a bit of time. Just overall, this one takes only about, 180 seconds to get to 400 degrees. Substance B takes about 310 seconds to get to 400 degrees. And here we are, we're off the charts with substance C. It still hasn't gotten to 400 degrees. So which substance has the highest specific heat? It's going to be C because it's taking longer. It's resisting heating more than substance A and B. Which substance has the lowest specific heat? The one that really is the most the least resistance to being heated. It heats up the fastest overall. It's going to be substance A. All right, and that's because we're seeing that it takes the least amount of time to get to that highest heat temperature. All right, last page. So this is part 7, and one of the things that we're doing with part 7 is there's just certain things that we want you to remember. So we need you to remember how to find the density of an object, and remember the formula for density is mass divided by volume. And hopefully you can manipulate that using, you'll have a density triangle on your, as part of your test tomorrow. You'll have that as one of your resources. So you have to remember how to manipulate that triangle. So remember, the triangle is essentially, there we go, mass, density, volume. So if we're trying to find density, we cover up it's mass divided by volume. I didn't draw you a very big triangle. If you're trying to find the mass, it's going to be density times volume. If you're trying to find the volume, it's mass divided by density. And so you just have to remember how to use that triangle. So there'll be, I think, at least one question where you have to deal with the density of an object. Question number 2 is, so we calculated the density. The mass is 45 grams. The volume is 122 milliliters. Density equals mass divided by volume, or 45 grams divided by 122 milliliters, which gives us a density of 0.37 grams per milliliter. The next question, this pertains to question 1, is, will the object from problem above sink or float in water? And I probably should have been more specific about that. Will it float in water? Explain your thinking. And I said it will float in water because its density is less than 1 gram per milliliter, which is the density of water. So this number, 0.37, is less than 1, the density of water, and as a result, it will float. If this number had been greater than 1, it would have sunk, and the farther, the more above 1 it is, the faster it sinks. Number 3, an object has a density of 1.8 grams per milliliter and a mass of 78 grams. What is the volume? And again, using our density triangle, we would have figured out that volume equals mass divided by density. And I can do that by just covering up my little v there, and then it's mass divided by density. Okay? The last thing we're doing is we're just doing conversions, and that's something that you would use your metric staircase. So I would give you something like 45 millimeters, and you would tell me that it's 4.5 centimeters. And I do that by simply moving my decimal, because I remember when it comes to my staircase, I guess I have my base units right here. And my base units, you guys, are meters for length. It is grams for mass. It is liters for volume. And I could add one more here. It is joules for energy. And then if I come down here, my unit is deci, small d. I go down one more, it's centi. And I go down one more, it's milli. I guess I can write those out. If I come up one, it's deca, capital D. If I go up one more, it's hecto. Oh, there goes my timer. It's time for dinner. Alexa, stop. Dinner time, hooray. And up here, it's kilo. So again, if I'm using my metric staircase and I want to know how many millimeters it is, well, first I have to remember that 45, the decimal, it's the same as saying like 45.0. And I'm starting at milli down here, and I'm moving to centi, which is one step up. So one step to the left, which means I'm going to move my decimal one place, which leaves me with 4.5 centimeters, which is what I've written here. So I've got the next one, B, 378 kilometers, is the same as saying how many meters. Well, I have 378. I'm going to do this up here. 378, which is the same as saying 378.0. And I want to find out how many meters. It means I have to go down. Well, look, meters is down here. It's one of my base units. So I have to move my decimal to the right 1, 2, 3 places. And if I do that, 1, 2, 3, I make my little hammocks here. And I fill up my hammocks with 0, and that decimal just becomes a comma, and I end up with 378,000 meters. 9,126 meters is how many decameters, and again, I'm using that capital D for deca. Same thing. I start with my decimal is essentially here, and I'm going from my base unit of meters over one to the right. So if I move that decimal, then it becomes 912.6 decameters. So you get the idea here. Now, one of the things I want to point out, this last one, joules. Joules is the same as any of these base units, okay? So if I have 122 joules, that's the same as saying 122.0 joules. And if I'm going from just joules, my base unit, to millijoules, which is going to be down here, that means I'm going to be, oh, I did that the wrong way. Joules to millijoules. No, I didn't. So that means I'm going to be moving my decimal to the right 1, 2, 3 places. 1, 2, 3. Add up those zeros. And then there's my final answer, 122,000 millijoules. All right, so just those little things that we were remembering how to do on this last page. So anyway, that is the key. That's, if you have any questions, let me know. But like I said, the key is already posted, and I will add this video soon.